my talk. The aim of my talk is to introduce you content of our recent article. The topic is about molecule detection for single molecule localization microscopy. The talk is divided into two parts. In the first part, which is introductory part, I will repeat some basics about single molecule localization microscopy, SMLM. In the next part, I will talk more about the content of the article. Also, my colleague asked me or explained me that there is a tradition to bring something sweet, so please, something I don't pay. Don't worry.
How long did it take to choose it?
It was Kai's idea, I think. Okay, so let's go through SMLM. I will describe the method as a modification of fluorescent microscopy with all goodies that we like, such as we have nice contrast, we have a single molecule sensitivity, we have tools to target molecules we like in a somewhat specific way, using labeling or genetic modification methods, for example. Important feature of the method is that it provides resolution roughly around 10 millimeters. The method is relatively cheap compared to other methods with a similar resolution. First papers appeared around 2006, and the method is somewhat popular due to the Nobel Prize that it received 8 years later. Nowadays, SMLM basically means it's like a label for many methods such as palm, F-palm, storm, D-storm, and others. When we talk about 10 nanometer resolution, it's good to keep in mind some, I would say, basic examples of the scale we are talking about. So here I think my list of favorites. For 1 millimeter, it's the smallest step in a ruler. 10 times smaller is, for example, roughly human hair. 10 times smaller is large cell, such as red blood cell. This is something we have a hard time to see without using a microscope, because there's something like the limit of our eye. 10 times smaller is, for example, bacteria. And if we go below this scale, we hit a phenomenon called diffraction limit, which is basically due to the manifestation of a wave phenomenon of light that is barrier. We have a problem to see in microscope. Below this barrier, there are many, I would simply say, the molecular life lives in a nanoscale. We have viruses like here, COVID-19, interiors of cells such as mitochondria, and below that, the antibodies, proteins, molecules, and atoms. So to sum it up, microscopists or people, biologists, would love to see what's happening at the nanoscale. Ideally, the method should not disturb what's going on. We also would like to see it in a real time. For example, the protein fold quickly within a second. So let's go back to SMLM. It's called a super resolution technique, nanoscope, due to the fact that the resolution is below diffraction limit. The diffraction limit is basically given by the width of a point spread function of the microscope. The literature call it resolution due to Claire or Rayleigh, roughly around 1.5 or 250 nanometers. Here's an example. Our points per function of microscope, if we have somewhat ideal system, looks like this blobby function called area function. This function has a certain width, and this is what's called diffraction limit. That's source of diffraction limit, our limit in resolution. What's interesting from my perspective is that this idea of super resolution also exists in other fields. In image processing, we discuss the convolution. In spectral analysis, we, for example, use what's called autoregressive models, or many other methods, mathematical, based on compressed sensing, or matrix analysis, that propose tricks to get a resolution that is better than the width of a function. Basically, whenever we have an object of interest we are looking on that it's blurred by a known function, there might exist tricks to go around and get a better resolution. In SMLM, the principle of getting better resolution is based on the fact that we compute the position of molecules with a precision much better than the width of a point spread function if, on condition, that they are emitting in a sparse, non-overlapping way. Here is an example. We have our object of interest. If all the fluorophores attached to the object of interest shine at the same time, and once we obtain an image that is convolution of point spread function with the object, which is blurred by point spread function. In contrast, in SMLM, we process a video of images, an image sequence, where only a sparse subset of images are active, such that they do not overlap. And in this case, it's not too difficult to detect these molecules and find a position with better precision that's the width of function. We are essentially exchanging time resolution for space resolution. Now, how to do it? There are many methods how to make emitters to be sparsely active. Historically, the way people do it was based on the fact that some certain fluorophores can be activated or switched to the active state using a light. They can be photoactivated, or, for example, in our group, we use a DNA paint method based on DNA origami technique. This is the last slide about SMLM method in general. SMLM method is a computational method where we compute the super resolution image based on image processing. This is a typical operation that is done by computer. First, the raw image. This is noisy. The image is filtered such that the noise is somewhat removed. The molecules, or the intensity of molecules, are enhanced as much as possible, and sometimes the illumination of light is not perfectly homogeneous, it's not perfectly uniform, so it makes sense to subtract it before next steps, which is thresholding, where we say what's above the threshold is our molecule of interest. This molecule is then further processed by what's called a localization algorithm that computes the molecule position in a sub-diffraction precise way. Last steps, here called as post-processing, includes many other operations, such as drift correction. Basically, in SMLM, we record an image sequence which takes easily minutes or longer, but needs to be perfectly aligned, otherwise we will see some artifacts or not see the objects of interest. And there are ways how to correct it even in image processing by algorithms. Also, we would like to, when we would like to get super resolved image, we discuss an algorithm for rendering that computes the super resolved image based on the set of localizations. I would also say some more evolved post-processing methods include, for example, molecular kind. These techniques are close to fluorescence information spectroscopy. We have expertise here, or we are able to track molecules, how the molecule diffuse in time, and analyze this diffusion patterns. Others. Okay. Now, if there is no question about SMLM, we're more focused on the article. All right. So in our work, we focus on in the data processing chain on the first part, where we want to obtain. We want to detect our molecules. So the goal of the detection algorithm is from the input, which is noisy, maybe with not ideal background, obtained position of molecules that picks where they are. And in our work, we focus on this part because we find out when we were using current SMLM softwares that there are few things we would like to somewhat improve, or we see there's a potential for bringing something beneficial and new to the community. There are three issues we find. First one, literature or SMLM software use many different image processing filters. Yeah, so an obvious task was we compare all of them on the same data. We created some synthetic data. We used publicly available data, which were community approved somewhat. And then we also illustrate or measure the filter performance over experimental data that we recorded here at Microscopy. Core part of our approach was based on detection theory, like mathematical statistical theory that can provide tools that allows us to say that something is optimal in some sense. So we use the theory, we derive what is here called optimal filter with the highest performance, highest detection probability, and this filter served as a benchmark to other filters. So we compare all the filters, we know which perform the best, and then we find out like a performance upper bound, so we know how far or close is the current methods to the theoretical limit. Some of the filters not only remove noise and increase signal, some of them also remove non-uniform background. So, and some filters do not do that. So we were inspired from the radar field where I worked a couple of years ago, and adapted what's called an adaptive thresholding operation which adapts to potentially non-uniform background in such a way that then any filter can handle non-uniform background. Yeah. And the last issue we found out was that, especially in software, people tend to set a detection threshold intuitively based on absolute value of image pixels, or 3 sigma rule is used, so based on the noise standard deviation or SNR, and confirm the threshold level in somewhat subjective way. People oftentimes, for example, in 3 sigma rule, you have an option. If you have nice data, you use 3 sigma. But if the data are somewhat not nice, then people use 2 sigmas. And this 2 sigmas or 3 sigmas is basically a parameter that one needs to choose. And it's very subjective. So sometimes user use 2 and then look to the preview in the software where you can see how many molecules were marked as detection and how many of them are missed and how many of apparently noise signal is marked as detection. So we propose a solution that is user unbiased, and it's a common technique in other fields, using different names. So in statistics, people set decision threshold based on what's called significance level. In electroengineering, radars, and wireless communication, the term false alarm probability is proposed. In medicine, we use p-value threshold. What's nice is that even here at the Hayrovsky Institute, we have a spam filter with the threshold described by false alarm probability. So in our IT department use this. But this technique is not so common as we would like to be in SMLM community. Another positive implication is that if people use false positive probability as a decision threshold, it will also tell us how many false positive molecules we will have in the post-processing stage. False positive act as a noise in the post-processing. It's very useful when we, for example, developing new algorithms to know what's the level of the noise. This is a part I think this can be researched much more, because, for example, there exist many diffraction algorithms that usually compare 2 methods over some data set. It's unknown how much false positive noise was there. So I can easily see there will be algorithm that is good in a low noise condition, or in algorithms that is good when there is a lot of noise. So there will be like, I don't know. There will be like a trade-off between robustness and performance. So let me spend a few words about the core technique we used in the article, which is detection theory. In statistics, it's called hypothesis testing. This theory can give us a few useful tools, such as Niemann-Persson lemma. Basically, this lemma say that the test with the highest detection probability is given by a ratio of likelihood functions. Here, a likelihood function is basically conditional probability of received our measured image on condition of hypothesis 1, which is signal percent. Hypothesis 0 is signal absent, so it's a noisy background. If this ratio of 2 numbers is higher than decision threshold tau, then the test optimally say that the signal is there, otherwise we refuse the signal presence hypothesis. And what's nice about likelihoods is that once we know, we have an idea how the signal was created. In microscopy, we model the microscope as a linear system plus background plus noise. And even it's fine enough that we have a rough idea of how the signal was created, because there are ways how to handle if some numbers, some parameters of the model are unknown, like position of molecules and noise, variance of the noise. The theory provides us many tools how to handle these unknown parameters, such as to find out if there exists a test that is not dependent on the unknown parameters, or we can use Bayesian, I would call it also machine learning approaches. If we have some idea how the parameter is distributed, we can average the parameter out. Or like engineering improved approach is to replace unknown parameters by estimates. This approach is called generalized likelihood ratio test. It's the method we use in the paper. The implementation is straightforward. Unfortunately, the optimality of the test, as we have here, is not present anymore, but in practice it works very well. An example of this type of detection test is when we insert a model of microscope plus basic potential noise, which is Poisson distributed, we obtain a somewhat ideal filter that's called Poisson match filter. This is the filter we used as a performance benchmark. Now, interestingly, this approach, this filter, has been published in other fields, but luckily not in microscopy, so we can have the paper. The existing, these are the filters used in the literature. Some of them are well known from rich processing, like mini filter or Gaussian filter. Some of the filters not only remove noise and signal, but also remove ground. The idea here is if we estimate the ground by filter with a large size, let's say, then subtract this background estimate and then filter again with a smaller filter size that's, due to the thing that we know how large the molecules are. This all is linear operation and can be implemented as a one filter. So this is, for example, an example with difference of 5 milligreen filter. We take large filter, subtract the small one, and it's still a one linear filter. Now, there were some interesting discoveries when we, for example, compare our proposed Poisson match filter and compare it to a method called match filter. Match filter, not commented, is a Gaussian filter, when our microscope has Gaussian type of positive function. Yeah, in this case, we find out that the Poisson match filter, the optimal filter in Poisson noise system, is close to match filter for certain values of signal to background ratio. It's very interesting. Now, let me comment a thresholding type we proposed. We call it probabilistic thresholding. So the thresholding in general wants to balance between two types of error that can happen in detection. One error type error is when we marked a noisy background as a molecule. The other type of noise, and this is false positive detection. The other type of error is false negative when we do not mark, this is very well visible, but here is a molecule that's not being marked as a detection, and this is an example of false and negative. Probabilistic thresholding is a thresholding that is based on a level of false positive probability which is a parameter to describe, we propose to describe thresholding methods. Here we have, on the right, we have two histograms of pixel values for this is hypothesis 0, which means noisy background. And these pixels are when the molecule is there. So for example, this threshold, if it's here, means that all the noisy backgrounds that are above the threshold are marked as false positives. We can set this probabilistic threshold once we know statistics of noisy background. That is typically just camera dependent. Once we know that we have CCD camera or EMCCD camera, we have an idea how this histogram looks like, and therefore we can easily find a threshold corresponding to false positive probability. There's like one-to-one mapping between them. We do the thresholding, or there's an option to use thresholding locally adapting to potential non-uniform background. And this is the idea we adopted from radar. It's, I would say, the best described by examples. So on the left, we have a non-uniform background where the decision threshold is constant for every pixel. So we can see that in this bar, where the background is somewhat higher, we have many false positive detections. In contrast, here we see how the performance detection look like when we set the decision threshold, always locally adapting to the background around the model. It can be also implemented efficiently as one filter with the following. Usually, when we have our pixel we want to test, with this pixel, we look around in the yellow area, take the pixels from here, and get the noise statistics and use it in a thresholding here. We usually omit the part around the pixel because we accept that the molecule has a certain size, and the pixels here are more affected to the molecule. For evaluation of filter performance, we choose a performance metric called receiver operating characteristic, which is basically a plot of detection probability against false positive probability. It's somewhat typical tool when we look to the detection to the books about detection theory, but this is not a common metric used in the SMLM community, due to the reason that in image processing we oftentimes deal with similar problem, which is called image segmentation, where we actually want to mark the certain pixels as a foreground and certain pixels as a background. So here we have an example of an image which is called reference, where the foreground are marked by dark color is a white color pixels. And if we have one prediction algorithm here, there's one, the prediction is marked by orange color. There is a somewhat large overlap between the ground truth. So if we compute performance metric based on the overlap, like the dice score, we obtain 92%, which is very, very good. Unfortunately, when we focus on how many objects are there, because in SMLM, after the detection process, we are applying the localization algorithm looking for the super-resolved molecule position. Then this approach is very suboptimal. We found only one object out of 3. So contra example is a prediction algorithm number 2, which has much loosely overlap metric because we are missing these pixels. These are in addition there, but we found out all 3 objects. So this one actually is much better, even though the overlap metric is 80%. Yeah, we evaluate the performance by Monte Carlo simulations, which means we synthetic the data with a single molecule, so we can say we avoid some issues with when 2 molecules are mapping. We tested a case with uniform background and with background that is parabolically nonlinearly non-uniform. And here are some of the results, how it looks like. So ROC metric we use is a plot of detection probability against a false positive probability. False positive probability is a parameter of algorithm we choose. So we usually fix 10 to the minus 4 and then compare all other filtering methods based on which one has the highest detection probability. So the higher the filter perform, the better. The more close the probability to 100, the better. So we confirm that the theoretical partial match filter performed the best. It performed identically to match filter, and all the other methods are somewhat performing lower. The last one is no filter, where we do no filter. A similar conclusion we can find based on our synthetic data with uniform background. Here we use adaptive thresholding operations, so even the filters that do not remove background perform nicely. Yeah, and very much similar results we've obtained for publicly available, community-approved data sets that come from a SMLM challenge in 2013 and 2016. And the last data we've tested were based on our experiment. When you present a result with a theoretical based result, the most often times or very often question is, which is very perfectly relevant, is how it performs in the lab, in the non-synthetic data. One problem in evaluating on experimental data is that in order to quantitatively say compare the methods, we need to know the ground truth, where the molecule actually was, and this is impossible. So we proposed a trick, or also proposed in other papers, where we measure our sample in a perfect single background condition, SNR conditions, and take this measurement as a ground truth and compare it to the measurement where conditions were much poorer with an additional interference. So, and this comes me to the conclusion. So we hoped that our results bring some new insights into the detection methods currently used in SMLM. If it's been used in the community or as part of the SMLM software, it would somewhat lower the demands on user. For example, nowadays when we use SMLM processing, for example, in thunderstorm, user needs to say which filter out of many to use. The filters also has certain parameters, like Gaussian filter has a sigma, for example. And in contrast to that, we advocate that instead of this, we would prefer to use a single filter with a single parameter that is our false positive probability. So if it's adopted, then also the SMLM software development would be somewhat easier, and it would help when comparing different results of different research groups. Because nowadays, different groups use different software where the threshold is set different way. They use different filters. So it would be nice if it's somewhat more harmonized. Based on our data, we find out that the meshed filter with adaptive thresholding or lowered Gaussian filter with the static thresholding perform the best. Yeah, the limitation on the method is, but it's not. Well, yeah, it's not limitation of the method, but I see as one thing that maybe is the reason why people don't study it in more detail in previously, which is basically that in the SMLM, we are focused on the highest possible resolution. In this case, we basically want only the brightest molecules. And these brightest molecules are not difficult to detect. So the method or the approach we presented would be much more useful if we are playing with the crappy data, averagely bright molecules. Because nowadays, what people often do is that after the detection and localization processes, few of them, 10 to 20% of data are discarded from the localization because they are not bright enough. So, of course, there are methods. If we, for example, take 5 medium level bright detections and are able to say that they come from the same source, we can collect the photons from them and obtain one good localization. So, like in method, RASI method, that's related to this article. The last thing, which is not a limitation, but our method is based on the assumption that the emitters are not overlapping. So the question, how the detection filter should look like when we have high density emitter data, this is still an open question to be researched. So thank you for your attention, and I'm very happy for your insights or comments.
Thank you very much for your interesting talk, and also congratulations on an article with quite high relevance in my point of view, because like those detection limits and so on are quite important and somehow in my point of view a little bit overlooked. So are there any questions? I have seen one hand already.
Thank you for your talk. I have a very practical question. We are using the thunderstorm for our image analysis. So what can we take from you? Like, do you have the software? Is it like a protocol how to analyze the data? Can we implement it in the thunderstorm or?
We would love to be implemented this idea in as many software as possible. The thing is, we're also using thunderstorm. And the situation is not very happy because since 2016 nobody is taking.
Yes, I'm also not very happy because it's not working with my computer.
Yeah. Yeah, it's open challenge.
So this is kind of a protocol how to analyze the data, and the software is still developed.
The idea is that here we put all the equations and derivations on the desk, and now it would be nice to have 1-2 talented programmers to include it in the software. Otherwise, paper is nice, but if people start using it, it would be nicer.
Yes, I agree. Thank you.
And how is it with like some computational challenges for computers with this local adaptive thresholding? It must be a little bit harder for the PCs, right?
It depends.
Uh-huh.
It's when you design a new algorithm, there are always three things that you can compare the performance. One is how it actually works. The other one is complexity, how long it takes PC to process, and also how difficult the theory is, how long you need to spend to be able to implement it. And the last one is what's I would call something like a robustness. Some of the methods are developed to work nicely for Gaussian noise, for example, but it may fail in other cases. So in adaptive thresholding, you have an options to implement it as a linear filter, which means very fast, there is no issue with complexity. But what can happen is that it works nicely if it's under the condition it's been developed for, but once there are more dense emitters, it could be more robust if it's implemented as not a linear filter, but a median filter, non-linear filter. That can, and now it depends where it's implemented. For example, median filtering in Python works okay-ish, but in other software it may not work nicely. And there is another issue that, for example, there are papers saying we have a very fast implementation of median filter, but it's on paper, it's not implemented in Python, or there can be a patent Adobe, for example.
So it's also kind of dependent on the software where you would implement that,
Yes.
and it should be also accompanied with some like guess of the robustness and so on. Like ideally.
Well, I would comment it like in theory, on paper. It's, for example, with the median, there exist very fast algorithms for adaptive median. But this algorithm is, for example, patented by Adobe. Yeah. Or it's not implemented in the software you like.
I see.
So,
Okay, some other questions?
Thank you for the nice talk. I didn't get quite the concept, but however, it means that first you come to the microscope and you need to characterize the background and the noise, right? And
no.
requirement.
The filter reader is also match filter. And it's true that the shape of the filter depends on parameters you don't know, how many photons or how the background is. It can be implemented, but we use it as a performance benchmark because other filters are more easy to implement. Like Gaussian, for example, Gaussian filter or match filter do not need to know the level of background. This parameter doesn't need to be estimated. Well, so yeah. If we use sparse and match filter, we would, for example, need to estimate a level of background. But we don't have to, because based on the performance here, we see that performance benchmark, also match filter, perform almost the same as match filter. So it makes more sense to use more match filter, which is easier to implement.
Okay, thank you.
By the way, why we should use net gradient filter, which is almost the same as no filter?
Oh, that's
You shouldn't.
You should. Easy answer. Because even in some images it seems same or even worse in one of the images, which is like weird.
net gradient filter is used in Picasso, which is popular in DNA patterns. I've even talked to the guy developing the software, and he said, "Yes, we know about it." We would like to implement it, but you know, doing PhD and developing software is it's not easy.
Yeah.
For software, you don't get much.
So the result is it would need some improvement to be useful, right?
You mean the net gradient?
Yeah.
I just don't think it works so nicely.
Okay.
Well, these data sets includes the molecules that are not super shining.
Okay.
If we compare performance on the metals with super shining molecules, that most of the filters will be very close to 100%, or the differences would be not so big.
Okay. And one more question on slide 19, if you can go. Yeah, you have here those two possible predictions. Is it somehow possible to combine them and join together advantages of the both of those models?
Yes.
Okay, thank you.
There exist AI algorithms called object detection that do both. That do image segmentation as well as detecting the objects that somewhat combine these two metrics.
So is it already done, like in the research in other groups?
Well, the questions of these metrics are known for decades.
Oh, okay.
It's just confusing that people are switching which one to use because it's not trivial question. There's a nice paper with 100 pages supplementary showing what problems if you choose, what are the problems when you choose the wrong metric image processing, shown by examples.
Okay.
So it's a known problem, but it's so messy. It's like p-value in medicine. It's like it's there. Some people use it right. Some.
Other questions or comments? If not, then thank you once again.